Okay, interpolation process. In interpolation process, it is exactly opposite of decimation. In decimation, what we have done is that we decrease the sampling rate of the given sequence by a factor t. Well, in the interpolation, it is kind of opposite. So here what we are going to do is that we are going to increase the sampling rate by an integer factor capital I. Okay, some books they use this interpolation factor as L also. So keep that in mind. And what do you mean by this interpolation? It's very simple. If you look at this particular definition, interpolation is just adding I minus 1 samples between two successive samples. We will see that we have done in the lab also. It is interpolation is to increase the sampling rate, and how do we achieve that? By adding I minus 1 samples between two successive samples, right? And now we will see in the next slide. Well, interpolation is basically a two-step process. Okay, so we have upsampling. When we say upsampling, it is stuffing zeros. You can see this highlighted text here. Upsampling is just stuffing zeros between successive samples, whereas next job is that whatever zeros we have stuffed or included between those samples, they are need to be converted into real samples. Okay, so that process we call fill in the zeros with real samples, and it is achieved through some sort of linear filtering, which we are going to see shortly. Okay, I'll repeat again. Upsampling is just adding zeros between samples, but then there is one extra step is there, that is filtering, which will convert these zeros into real samples. Okay, now let's talk about upsampler. Okay, so upsampler is basically, yeah, excuse me for that. Okay, upsampler, what it does, it will take the input sequence x of n, as you can see this arrow mark here, and which is in fact at rate fx, and then it converts that sequence into v of m, which is in fact at I into fx. That means the sampling rate has been increased by I times. So that's why it is called an upsampler. Now, if you look at this particular circle which I have drawn here, you can see that the output of the upsampler frequency is I fold or I times of the sampling frequency of the input. Now we know that just now, as I told you, the second bullet point here simply states the fact once more that we obtain V of M, that is the output of an upsampler, by stuffing or inserting I minus 1 zeros between successive samples of the input, that is X of n. Now, how do I write it mathematically? So here you can see this highlighted expression where you can see that this is how we write mathematically, and this particular expression x of m by I indicates that it's an expansion. So we are taking the sequence x of n, we are expanding it so that we have empty spaces where we can insert these zeros. Okay, so once again, so this expression is for expanding the sample sequence, and this particular expression where we stuff the zeros. Okay, now this is a very important expression for upsampling, and now let's look at one example. Okay, in this particular example, just a sec. Okay, here I have taken a sequence x of n, and as you can see the samples out there, and I would like to upsample by a factor of 2. Just now we have seen the definition of upsampling. Upsampling by a factor of I means we are going to add or insert zeros between successive samples. How many zeros we are going to insert? I minus 1. But here, as you can see, the I which I have taken is 2. So we are going to insert 2 minus 1, that is 1 0 between two successive samples. Now the red arrow is pointing towards my input sequence. Now you can see here that the zeros are being stuffed. Zeros are being stuffed or inserted between two successive samples, which is shown here using these pink arrows. Okay, now, well, the interpolation process though does not just stop here. We have to convert these zeros into real samples. So that is coming in the next. This red arrow is pointing out that, as you can see here, that zeros are being in fact converted into some real samples. Now if you look at these three pictures, as you can see, first one is a sequence, and second one, given sequence, second one is a zero stuffed one, and third sequence is where those zeros are being converted into real samples through some interpolation filter, so which we are going to see later. Okay, okay, is it clear? Shall I move ahead? Okay, at least nod your heads because I have muted you all. Show thumbs up. Right, okay, I'm moving forward. Okay, next, this is very important. Now, so far what we have done is the time domain analysis. Means, once again, here this expression is about time domain analysis of the upsampler. Okay, but now we are moving from time domain to frequency domain. So now we will see what exactly happens in frequency domain when you upsample a sequence. Now here you can see, well, again there are three steps are involved. We know that our sequence upsample sequence is V of m, so we have to find it out first. That is step 1. And step 2 is we have to apply jet transform so that we can convert from time domain to frequency domain. And finally we have to get the DTFT, right? So that's our real frequency domain. To get DTFT, we have to replace z with e power j omega, omega x or omega y appropriately. We have to substitute to get the v of omega y. Now let's begin with the first step. In the first step, what I have done, okay, I did not highlight it, but here you can see here this particular step, here you can see that this expression I have given you earlier, right? So whenever we say an upsampler in time domain, we are going to replace the n with n by I. So here it does not really matter what independent variable you are taking n, m, x, y does not really matter. Just to differentiate with n and m, I have taken m here. So v of m is our upsample signal, which is in fact x of m by I, which we have defined earlier. Now we are going to apply jet transform onto that. So this is the definition of a jet transform. You take the sequence, you multiply with z power minus m or n, and apply summation over minus infinity to plus infinity. So here we are doing that, and in the next step, as you can see, here this step is important, and just look at the step just right above it. And here what I'm doing is that there you have x m by I want to get rid of it, so I'm replacing m by I with m. So this particular z of minus m becomes z of minus mi. Now these things you have to work on, and then if you have any doubt you can ask me in person. And then as you can see here, okay, this particular expression, now you can see that expression right above it, in fact a z transform, but in the place of z power minus m, I have z power minus I, z power I whole power minus m. So that is like z transform of x of z power I. Now as I told you earlier, to get the DTFT or the frequency domain representation of the upsampler, we are going to replace the z with e power j omega y and e power j omega x, since it is input here. So here this expression I have got, and as I mentioned earlier, just for the sake of simplicity, we are not writing e power j omega y or e power j omega x. We are just writing v of omega y and x of omega x. And if you look at this particular expression, and this is a very important expression, we are going to spend some time here. And this expression tells us that what exactly happens to the spectrum in frequency domain. So when you upsample a sequence x of n, whose spectrum is x of omega x, and what exactly is happening to its spectrum? The spectrum is being increased by I folds. So which means that if you earlier had, let us say, two images or two copies of the spectrum, and if you upsample it by, let us say, 10 factor, and then the resultant spectrum will have 10 more copies of that particular spectrum, input spectrum. Okay, and here that is what I'm going to uh, explain you. Okay, is anyone waiting out there? Because I don't have anybody in waiting room. Okay, right. So again, now you look at these. This is the input spectrum, what I have just told you. Here, this is what I have told you, right? The output spectrum of an upsampler is what? I times I folded version of the input spectrum. So that thing we are going to see visually. Here, if you look at this particular spectrum, that is the input spectrum. And now what I'm going to do is that I am going to upsample it by a factor I. Now here you can see that the spectrum has been increased I folds. So the spectrum has been increased I times. So compared to decimation, in interpolation, there is no danger of aliasing effect, but here we will get the same spectrum gets repeated multiple times. So that is one problem with this upsampling operation. Now, yeah, same thing which I have said here. The output spectrum is compressed by a factor I, or you can say it's a I-fold increase in the spectral images. So why is it happening? So this is because of the insertion of zeros. So when you insert I minus 1 zeros between successive samples, that's what we are doing in time domain. We are inserting I minus 1 zeros. So what is the effect of it in frequency domain? The effect is seen as I-fold increase of spectrum. Okay, that is what is shown here, right? Now let's move on to interpolator. So far we talked about an upsampler. So once again, I'm just repeating it. Upsampler is just a digital system which takes an input x of n with a certain sampling rate, and it increases its sampling rate. So how does it do? By stuffing zeros. So in time domain, we see that effect as addition of or insertion of zeros. In frequency domain, we see the same effect as in repetition of the spectrum multiple times, I times. Okay. Now, well, we have next one is, this is upsampler. Next we have interpolator. So interpolator is basically an upsampler then followed by an ideal low pass filter. So this ideal low pass filter has a couple of benefits. First thing, it will help us convert those zero samples into real samples, and second benefit is that it will help us remove those extra images. Just now we have seen that it will generate I images, so it will help us get rid of those extra images, which will be seeing shortly. Okay, now, okay, as I said earlier, the need for an anti-imaging filter. So the counterpart of anti-aliasing filter in decimation process, here we call it anti-imaging filter, because of the fact that it will help us remove those extra images which are generated in the upsampling process. So, well, what should be the cutoff of this uh, anti-imaging filter? Obviously it's a low pass filter. The cutoff should be pi by I. Okay, so if your interpolation factor is I, then the cutoff should be pi by I. So this is contrast to the decimator, which uses a low pass filter with cutoff pi by d. Okay, now, well, let's look at one example, and this I have pulled it from internet. So in this particular example, they are using the notation L for interpolation instead of I. So just keep that in mind. Now here, this particular thing is our input signal spectrum. Now this is the spectrum of the upsampled one. As I told you earlier, here you can see the number of spectral images have been increased. Why? Because that upsampling process will increase the spectral images in frequency domain. But as you can see, I have same copy of information multiple times. So I really don't want these many images. So here what I'm doing, I'm just taking a low pass filter, ideal low pass filter with a cutoff of pi by I. Here it is written as pi by L because their notation is L here. And now what happens is that this particular low pass filter, so these are the extra images. Since I'm passing this with the low pass filter, and what happens is that here you can see those images. The images are pointed with red arrows, and the same images are being filtered out here. So that is the benefit of using or use of those anti-imaging filter. Okay, now let's, okay, I want you to solve this problem, so which will be, I'll be posting anyway. this. So you just solve it out. Now, okay, this is about what do you say, interpolation. So interpolation is, once again, interpolation is okay here. Okay, this particular slide has this interpolation related information. Here you can see interpolation is just upsampling by I, right? That is like inserting I minus 1 zeros between two successive samples, and it is its time domain representation is given here, and frequency domain representation is given here. And here you can see the anti-imaging filter. And one more thing about anti-imaging filter is that it has to have a gain of I. Okay, and well, now we will look. So we are done with interpolation. Now let's look at this particular example. And here, now I have this particular sequence, x of n is equals to 1 2 1 1 2, and I want to resample it by a factor 3 by 2. But so far, whatever sampling, resampling, that is sampling rate conversion process we have discussed, they only take integer values. If you want to decimate something by a factor of d has to be an integer. If you want to interpolate something by a factor of I has to be an integer. But sometimes we come across situations where a sampling factor, resampling factor can be a fraction. Okay, so it has to be a rational number, and but it can be a fraction. So in such cases, what exactly happens here? I have taken this particular example, which I have like this particular output. I have taken it from the MATLAB code, and if I use this particular code, it is giving me this particular output. Now what's happening here is the decimation is occurring or interpolation is happening. And if you look at these two diagrams, first one where I am pointing this laser pointer now, this particular um, diagram, as you can see, well, it has 5 samples. The picture right below it contains more than 5 samples. So what did it happen? Is it interpolation or upsampling or decimation or downsampling? So what in fact happened is here it got resampled by a factor of 3 by 2. Now let's look at another example. Here, same sequence, I have just reversed. Now it is being resampled by a factor of 2 by 3. So in the first example, the net effect is upsampling. As you can see, there are more samples than the input signal. In the second example, the net effect is decimation or downsampling. There are less samples than the original sequence. So this kind of sampling rate conversion is sometimes called resampling, and it is called sampling rate conversion by a rational factor. Okay, so sometimes it is called I by D conversion. So I is for interpolation and D is for decimation. So you have to understand this notation. It is always interpolation by decimation. That means interpolation occurs first, then decimation occurs. So, well, now if you look at this sampling rate conversion by a factor of I by D, and from now on I'll be calling just resampling by a factor I by D. is in fact a two-step process. As I said earlier, first we need to interpolate the sequence by a factor I, and then we need to decimate the uh, same sequence after interpolation by a factor t. So that means you interpolate it, then you decimate it. So there are a couple of filters, right? We know what is an interpolator. Okay, well, once again, so in other words, we can say that this resampling or sampling rate conversion by a factor of I by d is like cascading an interpolator with a decimator. And here you can see, but as you can see in this particular diagram, we have an interpolator which is in fact an upsampler followed by a low pass filter which is anti-aliasing filter with a cutoff of pi by I. And then whereas a decimator is an anti-aliasing filter then followed by an actual downsampler with a cutoff of pi by d, obviously. And both of these are low pass filters. So instead of having two low pass filters, what we can do is that we can replace these two low pass filter with one low pass filter, which we are going to see in the next slide. But if you look at this particular slide, you can see that the rate of the input is fx, and the rate of the rate mean, I mean sampling rate. The rate of the output sequence is fx times of I by d, hence the name I by d conversion. Okay. Now, if you look at this particular slide here, from the previous slide, we have seen that we have a couple of low pass filters which basically perform the same job. So instead of having anti-imaging and anti-aliasing filter, we can replace them with a single low pass filter, which we are doing here. But the important point here is that the cutoff frequency. The cutoff frequency, we have to take a minimum of pi by d pi by I. Here you can see the response of such a filter. So now this filter is kind of performs both the jobs, anti-imaging as well as anti-aliasing, depending upon what kind of I by d factor we are choosing. Okay. Now let's move to here. You can see I have replaced those two filters, low pass filters, with a single ideal low pass filter. Now, well, the filter behavior, as I said, I have replaced two filters with one filter, but how do they behave? So their behavior depends basically on the I by D ratio. If I is more than D, that means effectively interpolation is taking place. There is no decimation. So let us say if I'm choosing I to be 3, D to be 2. So the net samples will be more than the original samples. So there you have, it basically acts like an anti-imaging filter. Uh, Conversely, if the I is less than T, that means the decimation is predominant than the interpolation. That means the downsampling is happening, more downsampling is happening than the upsampling. So there we need an anti-aliasing filter. So it basically acts like an anti-aliasing filter when I is less than D, right? Now we have to do the time domain analysis, and we have to do the frequency domain analysis for this I by D resampler. So when you look at the time domain analysis, it's very simple. Here we are taking the sequence x of n, here you can see which is highlighted, and the first step what we are doing is upsampling. After upsampling, you're going to get V of k, that is intermediary signal. Okay, and then since we are sending through an ideal low pass filter, we can consider this particular process as a convolution. Filtering in frequency domain is like convolution in time domain. Now, after that, the next step is downsampling. So once again, I'm taking the input sequence, I'm upsampling it, I'm convolving it, and then I'm downsampling it to get the I by D resampled sequence. Now here again, these are the steps we have to follow. Here I'm doing upsampling. So this is the expression for upsampling, which we have seen in the previous slides as well. And here this is the expression for convolution. So I'm taking V of k, I'm convolving with a function of having impulse response h of n. So this is the expression for convolution. And finally, I'm using decimation. And we know that when you use decimation, we are going to write y of m is equals to some signal of m into the decimation factor t. And these expressions, you just go through them, you will understand. Now here, one example I would like to tell you, and here I'm taking the interpolation factor as 3 and decimation factor as 2. Here you can see this is the original sequence, and here the upsampled one. So as you can see, zeros have been stuffed. Since the I is 3, now I have 3 minus 1, that is 2 zeros have been stuffed between successive samples. Then I have sent it through a filter, so those zeros have been converted into real samples. Then finally I have decimated it by a factor of 2. So from each successive, from 2 successive samples, 1 sample has been dropped. Okay. And well, this is the example which we have here, and you just go through it once. And coming back to frequency domain analysis, same process, but here we are doing in frequency domain. So we are first doing upsampling, then as I said, convolution there is like filtering here, so convolution there is like multiplication here, and then we are doing the downsampling to get the final frequency domain representation of the resampled signal with I by D factor. Now here, yeah, this is upsampling, filtering, downsampling. Now these are the steps which I have used here. This is for upsampling. As you can see, when I say upsampling, the rate is increased by a factor I. And then filtering, convolution in time domain is like multiplication in frequency domain. Now here you can see I multiplied the filter. Now here filter have only the amplitude or the magnitude of I. That magnitude is multiplied with the incoming sequence from the upsampler, that is V of omega. In the last step, we have seen decimation. So we have seen for a decimation, what happens in frequency domain, it gets scaled, it gets shifted, and it gets stretched. So these three operations, as you can see, are being done on this particular sequence. Okay. Now, but here one more thing here, but since we have a kind of combination of anti-aliasing and anti-imaging filter, so that filter will make sure that none of the images will cross that particular filter. As a result, you will have this particular expression in the frequency domain. So it is scaled by I, it is scaled by D, that is I by D scaling in for the amplitude, as well as I by D scaling for the frequency also. Now you have to keep in mind that the frequency should be between 0 and minimum of pi by d comma pi by I, whichever is lower. Now this is kind of, once again I'll just walk you through this particular frequency domain analysis here. As you can see here, we are going to do the upsampling, then we are going to do the filtering, that is opposite of convolution, here multiplication, and then we are doing the downsampling. Those three steps have been given here. This is upsampling, that is the output frequency is in fact I times of the input frequency, and here filtering, the magnitude of the filter is just I, so it gets multiplied with I. Now this is a decimation process where we can see the frequency shifting, frequency scaling, as well as amplitude scaling. Those three expressions are written here. And as I just told you, this particular expression is because of the fact that we are using an anti-aliasing filter, which in fact will remove all the images or all the aliases of the actual spectrum. So as a result, we have only one image, which is in fact I by D increased. Okay, its sampling rate is its sampling rate is increased by a factor I, and it is being decreased by a factor D. And this is about what we can say is that the sampling rate conversion. So now once again I'll just give you the summary of this. Just watch it closely. When we talk about this summary, first let me begin with the decimation process. The decimation process, as you can see here, it's a decimation or downsampling by a factor D. Means what we are doing is that we are either taking every D sample, or we are dropping D-1 samples between successive samples. This is the time domain representation of it. As you can see, y of m or y of n does not really matter what you write here. Here y of m is given as x of dm. So sometimes this decimation is also known as time domain compression. And since it is compressed in time domain, it gets stretched in the frequency domain. And this is an expression where you can see the decimation in time domain will in fact result in three operations in frequency domain. One is scaling, that is amplitude scaling, that is 1 by D, which you can see in front of the sigma. And then you can see stretched, you can see omega x is in fact it is getting divided with D factor D. That means it is getting stretched in the frequency axis. And then as you can see, that particular factor omega minus 2 pi k, that means as k runs from minus infinity to plus infinity, it gets shifted in frequency domain. Now, well, anti-aliasing filter, the purpose of the anti-aliasing filter is that since here in decimation process, frequency getting stretched, we have to make sure that the adjacent bands will not overlap. So that's why what we do is that we are going to send our input signal through a filter with this kind of response, where anything above pi by D and below pi by D, that means either positive or negative, is being cut off. Okay, so only the frequencies between 0 and pi by D, plus or minus pi by D, are sent through. And well, the decimator, there is a slight difference between decimator and downsampler. A decimator is basically a anti-aliasing filter followed by a downsampler, and same thing can be applied to a interpolator. In fact, interpolator is here, as you can see, interpolator, we have, as you can see here, it is upsampling by a factor I. Means we are inserting I minus 1 zeros between two successive samples. And the same thing can be said about its time domain representation. Here in time domain representation, as you can see, this is how it is. The first expression corresponds to the expansion process.